The cosmos is a vast yet mysterious expanse brimming with phenomena that constantly defy our understanding. From the intricacies of quantum mechanics to the enigmatic properties of black holes, the universe presents a plethora of perplexing puzzles that stretch the limits of our comprehension. This video acts as a portal into the intricacies of the cosmos, shedding light on the mysteries and surreal contradictions that endure despite our earnest attempts to decipher them. In the early stages of the universe, things looked quite different. Gas and dark matter clouds were just starting to come together under the influence of gravity. This was also the time when the first stars, made up primarily of hydrogen and helium, began to form. Surprisingly, even at this early stage, some incredibly massive black holes, weighing up to 1 billion times the mass of our Sun, had already emerged. According to our current understanding of how black holes form and grow, it should take billions of years for a black hole to reach such immense proportions. However, since the universe is less than 1 billion years old, this poses a puzzle. According to existing models, quasars and other supermassive black holes shouldn't have existed during this early period. But observations tell us otherwise. So how did these colossal black holes come into being? How did they gain so much mass in such a short time? And what does this newfound information mean for our understanding of black hole formation? Before delving into those questions, let's clarify what a quasar is. A quasar is essentially a supermassive black hole that spins rapidly and consumes surrounding matter, emitting intense radiation in the process. They are incredibly bright and powerful cosmic phenomena, often billions of times brighter than our own Milky Way galaxy. The key to understanding their strength lies in their environment. Quasars are typically found in galaxies with abundant gas reservoirs. As this gas falls into the black hole, it heats up and emits radiation across various frequencies. This process occurs predominantly in distant galaxies because local supermassive black holes usually lack the necessary gas supply. For example, Markarian 231, one of the closest quasars, is still about 600 million light-years away. The question at hand is, how do black holes, these magnificent cosmic phenomena, come into existence? Currently, there are two primary theories explaining their formation. The first theory, widely accepted, suggests that when a massive star dies, it can collapse under its own gravity, forming a black hole. Initially, these black holes might have a mass up to about 100 times that of our Sun. Over time, they can grow larger as they consume nearby matter, eventually reaching a supermassive state with a mass millions to billions of times greater than the Sun. However, experts have determined that even with ample time, a black hole couldn't accumulate matter fast enough to grow to the size of 1 billion suns in just 500 million years. This is due to the formation of an accretion disk, a swirling ring of matter that forms around the black hole as it consumes material. The intense gravitational forces within this disk cause it to heat up and emit various types of radiation. This radiation exerts a powerful outward force which counteracts the inward pull of gravity, slowing down the rate at which the black hole can consume matter. This upper limit on a black hole's growth rate is known as the Eddington mass. Even if a black hole manages to consume matter at a rate exceeding this limit, the excess accumulation would likely result in powerful outflows of energy, blowing away nearby material and halting further growth. Thus, the growth rate of black holes is constrained by these factors. If this scenario occurs, it challenges the conventional understanding of how quasars, intensely bright objects powered by supermassive black holes, formed in the early universe. Now let's delve into an alternative theory explaining the origins of quasars. This hypothesis suggests that black holes ranging in mass up to 100,000 times that of the Sun could have formed from the collapse of short-lived stars. Some of these stars, possibly with lifespans nearing 250,000 years, might have collapsed into massive black holes. Given their enormous size, these black holes could have rapidly accumulated billions of times the mass of our Sun. Support for this idea comes from estimates indicating that quasars must have had initial masses between 10,000 and 100,000 times that of regular stars, which aligns with this hypothesis. However, for such colossal black holes to form, the parent stars would need to be incredibly massive, tens of thousands of times larger than the Sun. Yet, no such massive stars have been observed in our observable universe. Even the largest star on record is only about 300 times the size of our Sun. Nevertheless, conditions in the early universe differed significantly from what we observe today. Simulations suggest that under these early conditions, massive stars could have emerged at the convergence points of dense, turbulent streams of cold gas. While this scenario would have been rare, it provides a potential explanation. However, for stars to form under these circumstances, highly unusual conditions such as intense ultraviolet radiation or extremely fast movements between gas and dark matter would have been necessary. Moreover, none of the environments known to us today resemble those where the first quasars were discovered. So despite these challenges, how do we explain the appearance of quasars in the early universe? Scientists conducted simulations to address this question. Typically, a new star forms when a dense mass within a cool gas cloud collapses due to gravity. However, if there is significant turbulence present, this collapse can be disrupted. The simulation revealed that the turbulence caused by the intersection of streams prevented the formation of typical stars we see today. Instead, the cloud expanded to such an extent that it violently fragmented into two massive stars, approximately 31,000 and 40,000 times the mass of the Sun. In this scenario, if the gas from the streams continues to fuel the clouds, a supermassive black hole, billions of times the mass of the Sun, can develop and grow rapidly within a few 100 million years. This sheds light on how supermassive black holes could have formed at the intersections of gas streams, even without extraordinary circumstances. According to estimates, around 200 quasars could have emerged within the first billion years of the universe's existence. One of the study's authors, Daniel Whalen, summed it up by stating, "The first supermassive black holes were merely a natural result of structure formation in cold, dark matter cosmologies, offspring of the cosmic web." This concept is remarkable. If you're still watching, be sure to subscribe and like the video. Thank you so much. Let's continue. A supernova is like the grand finale of a star's life, marking its most spectacular and powerful moment. Picture this: a massive star, at least 5 times the size of our Sun, reaches the end of its life cycle and explodes in a colossal burst of energy and light. Now, what leads to this dramatic explosion? Well, massive stars are like cosmic powerhouses, burning through vast amounts of nuclear fuel at their cores. This process generates immense heat and pressure, which keeps the star from collapsing under its own gravity. It's a delicate balance between gravity trying to crush the star inward and the energy from nuclear reactions pushing outward. But eventually the star exhausts its nuclear fuel. With nothing left to sustain it, the balance is disrupted and gravity takes over. The star collapses in on itself with staggering speed, like a building crumbling in a fraction of a second. This collapse sends shock waves rippling outward, triggering the star's outer layers to erupt in a dazzling display of light and heat. What's left behind after this cosmic fireworks show is a dense core and a rapidly expanding cloud of hot gas known as a nebula. This remnant serves as a testament to the colossal forces at play in the universe, marking the end of one star's journey and the birth of something new amidst the chaos of creation. A supernova can result in the formation of incredibly dense objects called black holes, which are among the densest entities in the universe. Imagine yourself as an astronomer in the early 17th century, a time before the invention of telescopes. With limited tools, you're peering into the night sky, trying to uncover the mysteries of the cosmos. Then, one remarkable day, you witness an extraordinary sight. A new star appears, shining brighter than Venus and even visible during daylight. Over the following weeks, it remains prominent in the sky, gradually dimming but still perceptible. This phenomenon was observed by astronomers across Europe, the Middle East, and Asia, including the renowned Johannes Kepler in 1604. Today, we understand that what they witnessed was not the birth of a new star, but rather a supernova explosion, a colossal event marking the end of a star's life cycle. The most recent supernova observed within our own galaxy occurred in 1604. While it's possible that other supernovae have since occurred nearby, they may have gone unnoticed due to obscuration by interstellar gas and dust. The Crab Nebula serves as a poignant example, as it is the remnant of a supernova that exploded around the year 1054, its light reaching Earth centuries later. In 1987, astronomers observed a supernova in the Large Magellanic Cloud, providing a rare glimpse into a phenomenon akin to Kepler's supernova. Furthermore, astronomers have documented several supernovae in distant galaxies, although these can only be observed with the aid of telescopes. Such events would have eluded the observation of skywatchers in Kepler's era, highlighting the remarkable advancements in astronomical technology over the centuries. It's been a staggering 418 years since the last time we observed a star exploding in our galaxy. Considering that typically we expect between 1 to 3 such explosions every century, we're long overdue for a spectacular supernova event. Luckily, modern astronomers are in a far better position to study such an event than their predecessors like Kepler or scientists from just a few decades ago. Today's astronomers have access to advanced telescopes that can capture visible light, enabling them to simulate the experience of being near a supernova and observing it firsthand. Moreover, they also have tools sensitive to infrared light, which has longer wavelengths and can penetrate gas and dust more effectively than visible light. This capability allows astronomers to see objects that might be obscured from view with conventional telescopes. For instance, the James Webb Space Telescope primarily records in the infrared spectrum. Beyond light observation, modern detectors can capture other emissions from supernovas, such as neutrinos, which are subatomic particles, and gravitational waves, tiny vibrations in space-time. In the scientific realm, two main types of supernovas have been identified. Type 1 supernovas occur when a white dwarf star pulls material from a companion star until a runaway nuclear reaction blows the white dwarf apart. On the other hand, Type 2 supernovas happen when a star collapses under its gravity as it runs out of nuclear fuel, triggering a powerful explosion. In some cases, supernovae can outshine their entire host galaxies. Type 2 supernovae are particularly intriguing because they emit an immense amount of neutrinos along with light. Interestingly, neutrino emissions can start even before the explosion itself. Back in 1987, when neutrino research was still in its early stages, 3 detectors managed to capture about 24 neutrinos from a supernova explosion. If a similar event were to occur today within our galaxy, we could potentially detect hundreds or even thousands of neutrinos using the global network of detectors, offering significant insights. However, if a collapsing star forms a black hole instead of exploding, the emission of neutrinos abruptly stops. Detecting this sudden cessation of neutrinos could indicate the formation of a black hole. By comparing the missing star to entries in astronomical databases, we might identify it as the location of a newly formed black hole. Furthermore, if we were to successfully detect gravitational waves from such a galactic explosion, it would mark a significant achievement. Gravitational waves predicted by Einstein are ripples in spacetime caused by the acceleration of massive objects. They were first detected in 2015, primarily originating from mergers between black holes and neutron stars. This trifecta of discoveries, neutrinos, black holes, and gravitational waves, provides valuable insights into the universe's most dramatic events. When a supernova happens in our galaxy, it's a significant event that astronomers expect to observe. Despite astronomers using computer models to understand supernova explosions for years, many aspects of these events remain mysteries. However, studying gravitational wave data could provide valuable insights into this phenomenon. Concerning the potential threat to Earth from a nearby supernova, theoretically, it could pose a danger. However, the likelihood of this is currently low because there are no stars close enough to Earth that are at risk of exploding. Nonetheless, if a supernova did occur nearby, its radiation could be catastrophic. The release of harmful UV, X, and gamma radiation over several weeks could damage Earth's ozone layer. Even if these radiations didn't reach the surface, the depletion of the ozone layer would expose life on Earth to lethal levels of UV radiation from the sun, endangering everything from oceanic phytoplankton to humans. There's evidence suggesting that a supernova may have caused a mass extinction event around 360 million years ago, near the end of the Devonian period. However, supernovae aren't solely destructive. they also play a crucial role in the creation of new elements essential for life. Astronomers and physicists highlight that the nuclear processes occurring within exploding stars and the subsequent dispersal of heavy elements throughout space contribute to the formation of elements vital for human existence. In the broader narrative of the universe, supernovae serve as pivotal events. Approximately 13.7 billion years ago, the Big Bang set the universe in motion, initiating the formation of atoms, stars, and galaxies, marking the beginning of the cosmic tale. What unfolds here is a uniquely human saga, stretching across millennia as we strive to comprehend the universe. Guided by the principles of science, this endeavor has allowed us to grasp our position within the vast cosmos. Over thousands of years, we've meticulously recorded our observations of the heavens, amassing a library's worth of knowledge about the universe's origins and eventual fate. So where does our story begin? Let's embark on this journey from the very beginning, diving into the genesis, starting with the monumental event known as the Big Bang. The concept of the Big Bang serves as a framework for understanding the cosmic evolution, revealing how the universe transformed in an instant. Yet the exact cause of this cosmic genesis remains a puzzle to this day. As we gaze into the depths of the universe and ponder distant galaxies, we witness a captivating panorama of celestial motion. Everything seems to be moving away from us, expanding at incredible speeds. Tracing this expansion back, we glimpse a moment some 13 or 14 billion years ago when all matter was densely packed into an unimaginably small point. The Big Bang stands as our leading theory, a testament to our efforts to unlock the secrets of the universe's birth. For a long time, contemplating the universe's origin wasn't a widespread pursuit. Some paid it little mind, while others believed the cosmos had always existed, an eternal enigma. Initially, even scientists were cautious about embracing the concept of the Big Bang. Originally coined somewhat mockingly, the term itself presents a paradox. It wasn't exactly big, considering the belief that the universe began from a singularity and there was no literal bang, since there was no medium-like air to transmit sound vibrations. However, today, the Big Bang theory stands as a cornerstone of scientific understanding, widely accepted and comprehended. Yet, while the theory has solidified its place in our knowledge, it hasn't unveiled all the mysteries surrounding the birth of our cosmos. Traditional Big Bang theory doesn't address what initiated the event, why it happened, or what came before it. In the present moment, we inhabit the aftermath of the Big Bang. Everything we experience, sights, sounds, tastes, smells, and touches, is part of this aftermath. Here we are on Earth, a remarkable planet made up of silicon and oxygen, enveloping a metallic core. Its surface is adorned with vast oceans teeming with diverse life forms. In a graceful ballet, Earth completes a full rotation every 24 hours while orbiting the luminous star we call the Sun, completing a journey around it every 365 days. The Sun, a radiant behemoth primarily composed of hydrogen and helium, boasts a searing surface temperature approaching 10,000 degrees Fahrenheit. This cosmic furnace converts an astounding 700 million tons of hydrogen into 695 million tons of helium every single second. This radiant star lies at the core of our solar system, which formed around 4.5 billion years ago. Our solar system comprises 8 diverse planets, ranging from the scorching Mercury to the icy Neptune. But it's not a static entity. It hurtles through space at a remarkable 134 miles per second, nestled within the vast congregation of stars and systems known as the Milky Way galaxy. Within this galaxy, containing around 200 billion stars, an estimated 6 billion might possess planetary systems akin to ours. Our solar system, located on one of the Milky Way's outer arms, is just a small part of this grand cosmic ensemble. Yet the Milky Way is just a single entity among the immense expanse of over 125 billion galaxies in the observable universe. Indeed, the universe is vast, continually expanding. If we rewind time, we witness this expansion in reverse from cosmic to galactic scales, then to our solar system's dimensions, and further down to the scale of a studio, a coffee cup, and ultimately an atom. The universe's vastness unfolds before us, a cosmic narrative spanning unimaginable scales. Physicists have crafted an approximate timeline of significant cosmic events using telescope data and particle physics models from the universe's birth to its eventual demise. One pivotal moment was the cosmic inflation era, where the universe rapidly expanded. This period of inflation, though mostly theoretical, has gained traction among cosmologists as a possible explanation for the universe's uniformity across vast distances. Efforts to detect this expansion in early cosmic light were reported in 2014, although further investigation revealed that interplanetary dust was responsible for the observed phenomena. In the early stages of the cosmos, the temperature soared to a staggering 7 trillion to 10 trillion degrees Fahrenheit, or 4 trillion to 6 trillion degrees Celsius, just milliseconds after the Big Bang. At these extreme temperatures, quarks, fundamental particles typically confined within protons and neutrons, were liberated, roaming freely. These quarks joined forces with gluons, carriers of the strong force, in a primordial concoction that filled the entire universe. Scientists have recreated these conditions in terrestrial particle accelerators, mimicking the early cosmos. However, this fleeting state lasted only for a fraction of a second. Following the initial burst, the universe entered a period of intense activity, beginning roughly a few thousandths of a second after the Big Bang. As the universe expanded and cooled, it became conducive to the formation of protons and neutrons from quarks. Approximately 1 second after the Big Bang, the cosmic neutrino background emerged, a phenomenon yet to be directly detected, allowing neutrinos to traverse space without interaction. Within the first 3 minutes of the universe's existence, the fusion of protons and neutrons produced the isotope of hydrogen known as deuterium, along with helium and trace amounts of lithium. As temperatures cooled down, around 380,000 years post-Big Bang, hydrogen and helium atoms could finally bind with free electrons, forming the first neutral atoms. This significant transition marked the birth of the cosmic microwave background, first recognized in 1965. During this epoch, photons previously scattered by electrons could travel freely, creating the cosmic microwave background. Subsequently, the cosmos entered a phase known as the Dark Ages, a period of about 100 million years where virtually no light was emitted. Studying this era poses a formidable challenge, as astronomers rely heavily on starlight to unravel cosmic mysteries. The emergence of the first stars marked a pivotal moment around 180 million years after the Big Bang. As hydrogen and helium compressed into massive spheres, extreme temperatures formed at their cores. The intense radiation from these early stars and galaxies broke apart neutral hydrogen atoms, initiating a period known as cosmic dawn or reionization. Pinpointing the exact time frame of reionization is difficult due to its proximity to the Big Bang, with its signals obscured by subsequent cosmic phenomena. However, scientists estimate that reionization concluded roughly 500 million years post-Big Bang. Nearly a billion years after the Big Bang, supermassive black holes formed at the hearts of merging galaxies. Intensely luminous quasars, visible from distances of 12 billion light-years, illuminated the cosmos. Over the subsequent billions of years, the universe continued to evolve. Gravity drew material into denser regions, leading to the formation of galaxy clusters and vast filaments of gas and dust, creating the intricate cosmic web that we observe today. The birth of our solar system traces back approximately 4.5 billion years ago, when a swirling cloud of gas coalesced into a yellow star with encircling rings in a single galaxy. Over time, these rings merged to form the 8 planets of our solar system, along with numerous comets, asteroids, dwarf planets, and moons. The third planet from the Sun, Earth, either retained a significant amount of water during this process or received it later through collisions with icy comets. This watery world became the cradle for life, with primitive bacteria emerging between 3.8 and 3.5 billion years ago. From these humble beginnings, life on Earth evolved and flourished. Primitive organisms evolved into complex marine creatures and towering dinosaurs that roamed the land. Eventually, around 200,000 years ago, Homo sapiens emerged, upright beings capable of contemplating the mysteries of the universe and unraveling its origins. However, this isn't the end of the story. The future of the cosmos remains shrouded in uncertainty for physicists. Much depends on our ability to understand dark energy, the enigmatic force believed to be driving the universe's accelerated expansion. As we continue to explore and learn, the narrative of the cosmos continues to unfold, offering endless avenues for discovery and understanding. The fate of the universe holds various intriguing possibilities. If the universe continues to expand indefinitely, eventually all stars will burn out, and even black holes will fade away into nothingness. This would leave behind a desolate cosmos devoid of life, saturated with dormant energy. Alternatively, there's the concept of the Great Crunch, a scenario where gravity triumphs over the expansive force of dark energy, leading to a reversal of the Big Bang. Another possibility is the Great Rip, where the cosmos tears itself apart as dark energy accelerates everything to ever greater distances. The universe, vast and enigmatic, harbors countless wonders and secrets awaiting discovery. Among these mysteries, one of the most profound is the age of the universe itself. Scientists have dedicated decades to studying the cosmos, employing various tools and techniques to unlock its secrets. Through their efforts, they've estimated the universe's age to be approximately 13.8 billion years. The quest to determine the universe's age began in the early 20th century when astronomers recognized its expansion. Belgian astronomer Georges Lemaitre first proposed the idea of an expanding universe in 1927, but it was the work of American astronomer Edwin Hubble in the 1920s and 1930s that solidified this concept. Hubble's groundbreaking observations of distant galaxies revealed their recession velocities, establishing Hubble's law and confirming the universe's dynamic nature. The concept of an expanding universe naturally led scientists to ponder its age. Initially, attempts to estimate its age relied on models of stellar evolution. Scientists reasoned that by studying the properties of stars in our galaxy, they could gauge the universe's age, given the predictable sequence of changes stars undergo as they age. However, these early estimates were fraught with uncertainties due to gaps in our understanding of stellar evolution, resulting in wide-ranging estimates from a few million to several billion years. It wasn't until the 1960s that a more precise method emerged. In 1964, astronomers Arno Penzias and Robert Wilson stumbled upon a faint background radiation permeating all directions of the sky. This radiation, dubbed the cosmic microwave background, CMB, is believed to be residual radiation from the Big Bang, the universe's birth event. The discovery of the CMB was a watershed moment, offering scientists a potent tool for gauging the universe's age. By scrutinizing the properties of the CMB, scientists could glean vital insights into the early universe, including its temperature and composition. This data, in turn, enabled them to make more accurate estimates of the universe's age. In the ensuing decades, scientists honed their measurements of the cosmic microwave background, CMB, and deepened their grasp of the early universe. They also crafted more intricate models of cosmic evolution, incorporating the enigmatic influences of dark matter and dark energy, two substances dominating the cosmic landscape. By melding these refined observations with sophisticated models, scientists reached a consensus on the universe's age, 13.8 billion years. This estimate has received validation from various independent measurements, including studies of distant supernovae and the universe's large-scale structure. The age of the universe stands as one of cosmology's most firmly established truths, offering profound insights into the nature of the cosmos. The universe's age speaks volumes about its rich and intricate history, tracing back billions of years to a primordial epoch when the cosmos existed as a compact, searingly hot singularity. It signifies that the stars and galaxies we behold today are the outcome of eons of cosmic evolution, shaped by the relentless tug of gravity and the intricate interplay of matter and energy. The age of the universe serves as a vital clue in our quest to comprehend the cosmos, but it's just one fragment of a broader enigma. Cosmologists grapple with an array of profound inquiries. Why does the universe continue to expand at an accelerating pace? What lies at the heart of dark matter and dark energy? And how do they sculpt the universe's evolution? How did the earliest stars and galaxies come into being? And what characterized the universe in its nascent moments? These questions drive the relentless pursuit of knowledge in the field. One of the captivating aspects of the universe's age is its connection to the fundamental fabric of space and time. According to Einstein's theory of general relativity, space and time intertwine, forming a dynamic four-dimensional construct known as spacetime. This intricate fabric can be bent and twisted by the presence of matter and energy, giving rise to phenomena like gravitational waves and black holes. The age of the universe signifies that spacetime has undergone billions of years of evolution, responding to the cosmic forces by stretching and contorting. It underscores that the very essence of the universe has a narrative, and the structures we observe today emerge from the intricate interplay of spacetime, matter, and energy. While the universe presently expands at an accelerated rate, its ultimate destiny remains uncertain. Some theories propose a perpetual expansion, leading to a cold and desolate cosmos devoid of stellar brilliance. Others speculate on a cosmic contraction, culminating in a cataclysmic event akin to another Big Bang, birthing a new universe. Regardless of the universe's ultimate trajectory, its age reminds us of the extraordinary moment we inhabit in cosmic history. We exist in an era of perpetual change and evolution, where stars are born, galaxies collide, and the universe continues its inexorable march toward an uncertain future. Studying the universe and its evolution offers profound insights into the cosmos's fundamental nature and our role within it. The age of the universe serves as a gateway to understanding the potential existence of intelligent civilizations beyond our own realm. If life is widespread and the conditions for intelligent life exist elsewhere, there may be civilizations far older and more advanced than ours. Additionally, the universe's age guides our search for extraterrestrial life, informing us about the environments conducive to life's emergence by studying Earth's conditions and biodiversity. Some theories speculate on a multiverse, a vast network of parallel universes with distinct properties and histories. The age of our universe suggests that if a multiverse exists, numerous universes may have emerged over vast epochs, each with its own narrative and destiny. Lastly, contemplating the universe's age evokes a sense of awe and wonder. From the cosmic background radiation lingering since the Big Bang to the intricate ballet of stars and galaxies, the cosmos is a mesmerizing tapestry that humbles and inspires. The universe's age is a remarkable insight with profound implications for our understanding of existence. It sheds light on the universe's origins, the potential for extraterrestrial life, the fabric of reality, and the magnificence of the cosmos. As we continue our cosmic exploration, the age of the universe remains a beacon guiding us in unraveling the universe's mysteries and our place within it. The universe is a vast and complex place filled with phenomena that often defy our understanding. From the enigmatic workings of quantum mechanics to the peculiar nature of black holes, there are countless mysteries waiting to be unraveled. In this documentary, we delve into some of these perplexing aspects of the universe, shedding light on the strange paradoxes that challenge our comprehension. If you're intrigued by the mysteries of the cosmos, consider subscribing to our channel for more captivating content. One astonishing fact is that everything we currently comprehend about the universe represents just a tiny fraction, merely 5%. This portion consists of normal matter, which includes familiar particles like protons, neutrons, and electrons. However, the remaining 95% remains elusive, hidden in the shadows of the cosmos. This vast majority comprises dark matter, 27%, and dark energy, 68%, enigmatic entities that continue to baffle scientists. Dark matter, in particular, is a puzzling substance that behaves unlike any known form of matter. It doesn't interact with light or other electromagnetic radiation, making it invisible to traditional telescopes. Instead, its presence is inferred through its gravitational effects on visible matter, such as galaxies. Despite its prevalence, Constituting approximately 85% of all matter in the universe, its composition remains a mystery. Theories abound, ranging from hypothetical particles to exotic phenomena like primordial black holes. Similarly, dark energy adds another layer of complexity to our understanding of the cosmos. This mysterious force is believed to be responsible for the universe's accelerating expansion, but its true nature eludes us. Together, dark matter and dark energy represent the vast unknown, urging scientists to continue their quest for answers amidst the enigmatic depths of space. Dark energy is a speculative type of energy believed to saturate the vast expanse of space, driving the universe's accelerated expansion. Unlike dark matter, which exerts gravitational forces that slow this expansion, dark energy operates oppositely. It exerts a repulsive force, causing the universe to expand even faster. Despite its pivotal role, the precise nature of dark energy remains elusive. Scientists theorize it to be an inherent property of space itself, rather than a tangible form of matter or energy that can be directly observed. Current estimates suggest that dark energy constitutes approximately 68% of the total energy content of the universe. As for the universe's dimensions, our current understanding suggests it encompasses 3 spatial dimensions: length, width, and height, along with 1 dimension of time, culminating in what's known as 4-dimensional spacetime. However, theories such as string theory speculate the existence of additional dimensions, potentially up to 11 in total. These extra dimensions, if they exist, are postulated to be compactified or curled up to minuscule scales beyond our direct observation. Although we cannot perceive them directly, their influence on observable physical phenomena can be inferred. The proposal of these additional dimensions serves a crucial purpose in attempting to unify the mathematical frameworks governing the 4 fundamental forces of nature: the strong nuclear force, weak nuclear force, electromagnetic force, and gravity. The quest to discern the existence of these higher dimensions poses a tantalizing challenge. Can we detect their presence, or will we remain bound within the confines of our 4-dimensional reality indefinitely? The concept of the multiverse theory proposes that our universe is just one among many. This idea, embraced by modern cosmology and physics, suggests the existence of numerous parallel universes, each governed by its own set of unique properties and laws of physics. If this theory holds true, it would revolutionize our understanding of the cosmos and our position within it. One intriguing implication is its potential to elucidate the apparent fine-tuning of our universe to support life, a principle known as the anthropic principle. With countless universes boasting diverse physical laws, the likelihood of at least one nurturing life increases significantly. However, the multiverse theory also prompts profound questions regarding the nature of reality and our perception of what is real. If multiple universes exist with distinct physical laws, do they all possess equal reality, or is our universe privileged in its existence? Now consider time, an enigmatic aspect of our universe that perplexes researchers. Time is conceptualized as a measurable continuum devoid of spatial dimensions. It exhibits an unmistakable flow or direction, seemingly prohibiting backward travel. Are we ensnared in the unidirectional flow of time, forever moving forward? Is time's passage intricately intertwined with the fundamental workings of our universe? These questions delve into the very essence of existence and challenge our comprehension of the universe's fundamental properties. The theory of the Big Bang suggests that time itself began alongside the birth of the universe approximately 13.8 billion years ago. This concept raises the question, does it even make sense to inquire about what existed before this temporal inception? Time, a cornerstone of physics, is commonly defined as the sequential progression of events from the past through the present and into the future. It serves as a fundamental dimension within which events unfold, often depicted as a continuous line or axis. In the realm of physics, time is quantified in units such as seconds, minutes, hours, and years. Moreover, it constitutes a vital element of the space-time continuum, a 4-dimensional construct comprising 3 spatial dimensions and 1 temporal dimension. The trajectory of time is typically depicted as unidirectional, flowing forward without the possibility of reversal, a phenomenon known as the arrow of time. This arrow finds correlation with the second law of thermodynamics, asserting that entropy, a measure of disorder or randomness within a closed system, tends to increase over time. Despite these conceptual frameworks, the nature of time remains a subject of ongoing exploration and debate across the realms of physics and philosophy. Some theories postulate that time emerges as a consequence of intricate interactions among the universe's fundamental constituents. Conversely, others contend that time is an intrinsic property of the cosmos, analogous to space and matter. Quantum entanglement is a fascinating aspect of particle behavior that may seem to defy our understanding of the natural world. Essentially, it's when two particles become correlated in such a way that the state of one particle is immediately linked to the state of the other, regardless of the physical distance between them. This concept is consistent with the principles of quantum mechanics, even though it might appear to break traditional laws. However, it's crucial to clarify that quantum entanglement doesn't enable faster-than-light communication or disrupt causality. Despite the instantaneous correlation between entangled particles, we can't control or exploit this connection to transmit information at speeds exceeding that of light. This limitation is governed by the no-communication theorem in quantum mechanics, which asserts that such transmission is impossible. So, while quantum entanglement sparks curiosity and seems mysterious, it doesn't actually violate the laws of nature or the principles of causality. As for the questions about using quantum entanglement for instant communication across vast distances or the existence of life beyond Earth, those remain open to exploration. The universe is vast, containing at least 2 trillion galaxies, each potentially hosting numerous stars and planets. This abundance hints at the possibility of other life forms existing beyond our planet. The question of whether we are alone in the vast universe is a fascinating and profound inquiry. Despite the immense number of planets in our galaxy, Earth's seemingly ideal conditions for life suggest that we're not unique. But why haven't we encountered any other life forms? This conundrum is known as the Fermi paradox. There are several theories attempting to explain this paradox. One possibility is that life is indeed rare, requiring specific conditions to emerge. Another is that while life might be common, it struggles to progress to a point where it can communicate across vast distances. Additionally, civilizations may self-destruct before they can explore beyond their home planets. It's also plausible that we simply haven't searched in the right places yet. Understanding this paradox prompts us to ponder the future of humanity. If intelligent civilizations tend to falter before reaching out to the stars, what does that suggest for our own trajectory? Our quest to understand extraterrestrial life is constrained by our current technological capabilities, which are still rather limited. However, advancements in the future may unveil new techniques that could reveal evidence of life beyond Earth. But as we gaze outward into the cosmos, we must acknowledge a fundamental truth. We are not impartial spectators. As humans, we are intricately entwined with the universe we seek to explore. This self-reference poses a profound challenge to our perception. How can we claim neutrality when we are both observers and subjects of observation? This dilemma may skew our understanding, leading to misconceptions about the nature of the universe. The self-reference problem complicates our study of the cosmos. By acknowledging our inherent connection to the universe, we can strive for a more nuanced and accurate interpretation of the cosmos. Our fascination with the universe often leads us to focus on phenomena that directly impact our existence, potentially skewing our perception. But by acknowledging our biases and limitations, we can strive for a more objective and thorough approach to observation and analysis. Why does the universe seem tailor-made for us? This intriguing question has led to speculation about the fundamental constants of our universe, such as the speed of light, which seemingly allow for the existence of life. One explanation is the anthropic principle, suggesting that the universe appears finely tuned for life because we, as observers, exist within it. This concept, also known as the selection effect, implies that if the universe weren't conducive to life, we wouldn't be here to ponder its mysteries. Why is it easier to break things than to mend them? Entropy, a measure of disorder or randomness in a system, plays a crucial role here. In the universe, entropy tends to increase over time, leading to a progression from order to chaos. This explains why it's simple to shatter a window, but impossible to restore it to its original state. What does this mean for the future of the universe? As the universe expands, it heads towards a state of maximum entropy called the heat death, where everything becomes uniformly distributed and energy gradients vanish. This bleak scenario implies a cold, dark, and lifeless cosmos in the distant future. Though the universe isn't entirely closed, receiving energy from stars and other sources, the overall trend is towards greater disorder. However, this process unfolds over an incredibly lengthy timescale, likely spanning trillions of years. Now, can anything escape the clutches of a black hole? These enigmatic objects wield immense gravitational pull, even capturing light itself. While we've observed their effects and directly observed one, what occurs within their infinitely dense centers remains a mystery. Speculations about white holes, which could be the opposites of black holes, expelling matter and even time into our universe, further deepen the intrigue surrounding these cosmic phenomena. In the realm of physics, the grasp of a black hole is unyielding once an object crosses its event horizon, the boundary of no return. Here, the gravitational force is so intense that it distorts both space and time, drawing everything towards the singularity at the core, where conventional laws of physics falter. Yet what unfolds within the heart of a black hole remains an enigma. Our current physics fails to elucidate the conditions prevailing there, theorizing that the matter condenses into an infinitely dense singularity, devoid of volume. As for white holes, their existence remains purely speculative. These hypothetical counterparts to black holes are envisioned at the opposite end of hypothetical wormholes, bridges in space-time connecting distant points. However, empirical evidence supporting their existence, as well as that of wormholes, remains elusive. The cosmos teems with perplexing paradoxes, fueling our pursuit of understanding. As we probe the cosmos' outer reaches and delve into the depths of time, we encounter myriad mysteries. With each revelation, the universe unveils new layers of complexity, propelling us towards greater insights and discoveries. Once limited to our solar system's planets, our understanding has expanded to encompass a vast array of celestial bodies orbiting distant stars. These exoplanets, ranging from rocky terrains to colossal gas giants, offer a rich narrative of cosmic evolution. Originating from stellar remnants like dust and debris, their early histories were likely tumultuous, marked by violent processes. The universe, replete with galaxies, stars, and planets, reveals a diverse tapestry of cosmic landscapes. While our solar system boasts 8 worlds, it's a mere fraction of the countless planets dotting the cosmos. This realization marks a pivotal moment in scientific history, affirming the existence of planetary systems beyond our own. In the Milky Way alone, teeming with 200 billion stars, numerous planetary systems likely await discovery. In 2009, NASA launched the Kepler Space Telescope, embarking on a mission to unveil new planetary realms. Over the years, it has identified over 400 exoplanets, ranging from colossal gas giants dwarfing Jupiter to massive rocky worlds eclipsing Earth's size. Some trace chaotic paths perilously close to their stars, risking obliteration. Yet amidst this diversity, each planet stands as a unique entity. Despite their uniqueness, studying these distant worlds remains a formidable challenge due to their remoteness. Much of our understanding of planetary mechanics derives from our solar system's familiar 8. Here, 2 distinct classes emerge. The rocky quartet of inner planets, Mercury, Venus, Earth, and Mars, and the outer quartet of gas giants, Jupiter, Saturn, Uranus, and Neptune. Each of the 8 planets in our solar system boasts its own distinct identity, shaped by the unique conditions prevalent during the solar system's inception 4.6 billion years ago. The birth of our Sun triggered the dispersal of a vast cloud of gas and dust, serving as the cradle for all 8 planets, regardless of their proximity to the Sun or their composition, be it rocky or gaseous. Despite originating from the same cosmic materials, their formation occurred under vastly contrasting circumstances. Planets nearer to the Sun experienced scorching temperatures, while those farther away endured colder environments. These differing conditions influence the evolution of the planets, akin to ingredients baking into diverse concoctions in an oven. In the early solar system, a blend of silicate, water vapor, hydrogen, and methane pervaded the cosmic dust cloud. As planets formed, their compositions varied, reflecting the nuances of their respective environments. Close to the Sun, where heat was intense, volatile gases evaporated, leaving behind only materials resilient to high temperatures, namely rocks and metals. Consequently, rocky planets like Mercury, Venus, Earth, and Mars emerged in this scorching vicinity. Conversely, planets farther from the Sun underwent a different cooking process, leading to their distinct compositions. The composition of the cloud from which a solar system forms profoundly influences its planetary makeup. In some instances, a dearth of rocky materials may preclude the emergence of Earth-like planets, resulting instead in a prevalence of gas giants or a complete absence of rocky worlds. For rocky planets to form, the cloud must abound with metals and rocks, with subsequent steps involving a reduction in temperature. As the cloud cools, substances with high boiling points begin to condense into solid forms. Minute mineral grains emerge, serving as the rudimentary building blocks of nascent rocky planets. Over time, these grains coalesce through a process known as accretion, gradually accumulating mass. Initially, collisions between dust molecules foster the growth of larger particles, eventually culminating in the formation of rocks. Subsequent collisions between rocks lead to the creation of boulders, which in turn amalgamate into larger formations. Eventually, a critical mass is attained, enabling the nascent planet to exert gravitational pull, attracting nearby debris. Initially, numerous protoplanets vie for dominance within the solar system, potentially numbering in the hundreds. However, most fail to mature into fully fledged planets. A visit to the asteroid belt offers insights into the developmental stages of rocky planets. For instance, asteroid 4 Vesta, measuring a mere 329 miles across, falls short of the spherical shape characteristic of fully formed planets. To achieve this roundness, a growing planet must surpass a diameter of 500 miles, indicating the threshold at which gravitational forces crush it into a spherical form. Upon reaching a critical size, a young planet transitions from its irregular shape to a more spherical form. However, each collision with other celestial bodies generates significant heat, gradually melting the planet's surface. Amidst this turmoil, gravity plays a pivotal role, segregating heavier materials towards the core while lighter elements rise to form a crust. Yet this phase marks a tumultuous period, a time of chaos and upheaval that will ultimately determine a planet's fate. Originating from the same primordial cloud of dust and gas, each planet emerges with its unique characteristics, shaped by a combination of chance occurrences and the laws of physics and chemistry. Approximately 4.5 billion years ago, our solar system was a battleground, teeming with around 100 fledgling planets engaged in a frenzied demolition derby. Collisions were rampant, with many occurring during the final stages of planetary growth. As these collisions reshaped the planetary landscape, some bodies grew at the expense of others, gradually increasing in size. The larger planets began to gravitationally attract smaller bodies, leading to intense bombardment and the accumulation of space debris on their surfaces. When the chaos subsided, only 4 rocky planets remained, each bearing the scars of its tumultuous past. These formative experiences have endowed each planet with distinct characteristics. Mars, a desolate frozen wasteland; Earth, a vibrant hub of liquid water; Venus, a fiery realm dominated by volcanoes; and Mercury, a diminutive, scorched world devoid of atmosphere. Due to significant collisions in the past, celestial bodies like Mercury and Earth have undergone dramatic transformations. For instance, Mercury, with its thin crust and high density, suggests it could have been larger in the past. A collision at an angle likely stripped away its lighter crust, leaving behind the dense core we observe today. Similarly, Earth experienced a violent impact in its early history, resulting in the detachment of its mantle, which then coalesced to form the Moon. Mars also bears evidence of past collisions, with its northern hemisphere exhibiting thinner crust compared to the southern hemisphere. One hypothesis suggests a massive impact early in Mars's history removed a significant portion of its crust, leading to subsequent crustal buildup in the southern region. These collisions not only reduced the population of nascent planets, but also contributed additional materials to surviving celestial bodies. The composition of these materials played a crucial role in planetary development. Metal-rich chunks tended to sink towards the core during collisions, while lighter or icy components formed the crust. The rocky planets near the Sun, including Earth, were primarily composed of a solid iron core surrounded by liquid iron and molten rock, topped with a surface crust. Despite their shared origins, each rocky planet exhibits distinct characteristics in size and destiny. Although space appears empty, it's teeming with particles ejected from the Sun. The Sun's strong magnetic fields create solar winds composed of highly charged particles which shoot into space when these fields interact. Astronauts can perceive this phenomenon as a faint glow when they close their eyes due to energetic particles interacting with the fluid in their eyes, creating occasional flashes of light. Solar wind poses a significant threat to astronauts as exposure to higher levels could be fatal. An example of this danger occurred during the Apollo program when a solar explosion occurred between two moon missions. Had astronauts been present, they would have faced potentially lethal levels of radiation. However, the threat of solar radiation is mitigated here on Earth due to our protective magnetic field. This invisible shield, generated from the Earth's core, shields us from the harmful effects of the solar wind. As a result, while space is fraught with radiation hazards, we are relatively safe from them on our home planet. I'll leave it at that. Thank you so much for watching another documentary. Be sure to subscribe if you enjoy these astronomy documentaries. And with that being said, take care.